Well, good morning. It's only about half of us here so far, so hopefully others will be joining us, or maybe they'll be able to help teach this portion because they understand it so well. Who knows? But anyways, we'll go ahead and get started today. Today our topic is the emission spectrum, and we're just gonna review this information. For those of you that aren't aware, this is chapter 7 in your Bouchon. So if you hopefully you looked at it ahead of time. If you didn't, that's what you wanted to look at. But let's talk about a couple different things about the emission spectrum to start with. The first thing is what the emission spectrum actually is. And so we have to think about a couple things first before we go to narrow it down to the emission spectrum itself, okay? Is what we're talking about here is the quality and quantity of the X-ray beam itself, all right? So what we're looking at is first we have to have a filament current so that we induce thermionic emission, right? Because filament has to be heated up to a level that is able to boil off the electrons. And then we have tube current, which is responsible for the emission spectrum. And so tube current is that quantity of electrons that are moving from cathode to anode. Okay, that's what the tube current is. So when we make little minor changes in filament current represent big changes in tube current, because one's measured in ampere. So when we heat the filament just a little bit more, it's able to boil off a whole lot more electrons that increase the amount of tube current. Okay, so the biggest thing is that is the number of electrons that are going across from cathode to anode. Well, once we hit the anode, do all of those electrons that travel across the tube from cathode to anode result in X-rays being produced?
No.
Correct. So that's a big deal here, okay? Because they don't all represent X-rays being produced. So what's the majority of the interactions result in?
Characteristic
Say what, hon?
characteristic X-rays.
Okay, let's just think overall, okay? So when we talk about overall, we produce a lot more heat than anything, right? 99% of the interactions that occur at the target just result in infrared radiation or heat being produced. And only 1% of the interactions represent actual X-ray production. Okay, so the majority of the interactions just produce heat. So that's a big deal to us. So we say, okay, so when we're looking at that, we have a lot of heat that has to be dissipated. So we have to look at the fact that as tube current increases, so as the quantity of electrons traveling from cathode to anode increase, then so does the amount of heat that we produce, right? If we know that 99% of the interactions are going to be heat, then we know that as that number of projectile electrons increase, then so does the amount of heat that's being created. Does that make sense so far? Okay, that's the broader picture, okay? So then what we have to say there is, of the X-rays that are produced, if we don't know an energy, or we don't know the quality of the beam, then we don't even know if any of those would be characteristic. So, but we do know that at any energy level that will always be producing BREMs, because BREMs are not energy dependent. BREMs, X-rays are created at any energy level. So we'll always have BREMS X-rays, and only at specific energies. So that's when we look at this here, everything under this bell curve, this continuous spectrum, everything under that is BREMS right at this specific level, which is at the 69.5. That's the time we actually produce characteristics, is at that energy level. So if I have a KV of 68, I have no characteristic X-rays being produced. I have a completely BREMS beam, okay, because they occur at any energy level. Are you okay with that so far?
Yeah.
Okay, I was going to say that took a little longer to get an answer on. Okay, and if you need to stop me in between, go ahead and stop me. So we'll talk about the emission spectrum itself, okay? So when we talk about the y-axis, which is this one, the up and down, so it's the amplitude of this wave, okay? So the quantity is the number of X-rays that fall within this beam. So all the area under here, if we could color this a different color, everything under this counts as quantity, okay? So amplitude is talking about quantity of X-rays, so how far this arcs up and down. The beam's energy, so this is, quantity is directly related to mass, okay? So number of projectile electrons directly affect the number of X-rays that are produced. The x-axis here is the energy. So it's energy dependent, and that's why you have the discrete portion, this characteristic line, that's why you have it along the x-axis, because characteristic is energy dependent, okay? So anything that affects the quality of the beam will represent the shift of this bell. It'll represent a shift to the right if it's an increase in quality, and to the left if it represents a decrease in quality. Okay, and as far as amplitude goes, if the amplitude is less, then that means we have a lower quantity. If the amplitude is higher, then we would have more quantity. Everybody good so far on the basics?
Yes.
Okay. All right. Yeah, I'm trying to take it in little baby bites. So if I'm asking you more questions than normal, it's just because I want to make sure that I don't get to a point and then you had a question 10 things back and it didn't make sense back then. So, so first thing, again, heat's directly going to be directly related to the quantity. So this way, so if we have more X-ray quantity, we also had produced more heat. Whereas quality is a measurement of the efficiency of the equipment. So that means the energy of the beam, the penetrability of the actual X-ray beam. Those are energy related, quality related. So that's all about the efficiency of the X-ray equipment. So anything that affects the efficiency would affect the quality. So we have KPP that would affect the efficiency. The generator phase that we're using affects the efficiency, because that's all about how much voltage ripple we have. So how many times do we go from zero to peak to zero, because we'd have more low energy X-rays. And if we're not going to zero each time, then we're going to have a less voltage ripple, and we'll have a higher energy X-rays that are being produced more on the higher energy level. And then filtration will affect efficiency, because filtration will decrease the quantity of that beam by taking out low energy X-rays, and that will also result in an increase in the quality of the beam. So I have a image here a little bit further ahead of myself at the moment than I want to be, but just when we're talking about, because this tends to be one that gives people grief, when we talk about going, we double the added filtration. We do this to lower patient dose. Well, you see how when we added it, we took away a whole bunch of X-rays that were being produced, right? Because this curve has much lower amplitude. We still have the same energy level because we didn't change kV, we just changed the filtration. So we got rid of a lot of low energy X-rays that just cause patient dose, and we made this a more homogeneous beam. So the energy is compacted in a shorter range, so resulting in a higher energy beam or a harder beam. Okay? Everybody okay with that so far? Yes, Amy.
I have a question on the graph. So, if the filtration affects the energy, wouldn't it affect the x-axis, like going from side to side?
Well, it affects quantity, and it affects the only way that it actually affects the energy is, you see all these X-rays that were available over on this side that were all lower energy X-rays.
Yes.
Okay, they're all gone. So it made it a harder beam because it got rid of all these low energy ones before you hit this level. So a lot less low energy are coming through. So it just condensed the energy. If it changed it here, so the kV didn't change, right? So it stayed right there. So the peak energy was the same of the beam, but it's a harder beam. More of the X-rays have higher energy. So
Okay.
it does have that little tiny, it has to the right, but just recognize that on the overall energy, it doesn't change it because it doesn't have the power to change it.
Okay, so then the filtration will affect the amplitude.
It affects the amplitude and the position, because this represents that little bit of a shift to the right because we got rid of all these.
Okay, gotcha. Thank you.
You good with that?
Yep.
Okay. All right. So again, when we talk about tube current, I'm talking about the quantity, okay? So when I talk about tube current, I'm talking about something that's going to affect this, the amplitude here, okay? And tube current is specifically quantity, no effect on quality whatsoever. So if I just change, and I've got that back this way. If I just change my MA from a 200 MA to 400 MA, I increase the number of x-rays that I produce, and you can see that that's pretty smooth across the board as an increase because it's specifically just a quantity factor. So if I change mass, I just change quantity, no change, or amplitude, no change whatsoever in the quality of that beam. So I did put some information, just general stuff for the emission spectrum, that basically anytime you see an emission spectrum, all it is a graphic representation of the quantity and quality of a specific beam. Okay, and an X-ray beam's what we're talking about. So all these different graphs that we're looking at, we're just looking at how specific factors affect the quantity and quality of our X-ray beam. So that's all the more we're talking about in any of these emission spectrums, like when we looked at right up here and we looked at MA and we said, oh, that's just an amplitude shift. So if I went from 400 to 200, then I would say the amplitude was reduced because I reduced the quantity by half, okay? And going from the 200 to the 400, I doubled the amplitude because I increased the quantity. I doubled the quantity, okay? So we'll look later at shifts in kVp and stuff, but right now just keeping that thought in mind. So we're talking about how specific things change it. So then when we look at the energy axis or our x-axis, anything that affects the energy of the beam affects the x-axis, and x-axis is the quality, okay? So anytime we do something that affects the overall energy, like we did filtration, where we said we reduced the amplitude because we took away a bunch of X-ray photons, but we increase the quality because we have a harder beam, we have a higher concentration of energies between a specific level because it's taking out those low energy. So when we talk about something changing on the quality spectrum or x-axis, we talk about shifts to the left or right. Okay, and again, the y-axis is just a quantity that represents the amplitude. So anything below a specific curve is related to quantity and is counted as a measure of quantity. Okay, so some of the different things that affect the number of X-rays, we know that mass does directly, right? Hopefully that's a yes. We know that kVp will affect quantity, but kVp also affects the quality because it is a change in the energy of the beam. We know that filtration will decrease the quantity, but we know the other side of filtration is that it increases the quality. Generator phase is dependent on whether we're going up or down. If we increase the generator phase and go to a generator phase that has a lower voltage ripple, then we're going to increase both the quantity and quality of that beam. the target material that we use, we know we don't go from one type of target material to another, right? So all we can talk about when we're saying that is we can compare different target materials that are used in our modality. So we use tungsten, right? We don't change off the tungsten. So our characteristic X-ray, or the discrete portion of our beam, occurs at 69.5 kVp. That's when we'll actually have characteristic X-rays, is when we have projectile electrons that are interacting at that energy level. Okay, so but we'll have BREMs throughout. But one of the things that we recognize is, see, I'm trying to get to target material one so I can. There we go. Okay, so I can show you what I'm talking about. So this is a molybdenum target. For all of you that are aware already, a molybdenum target is used in MAMO. MAMO uses very low kVp and higher mass values. Okay, so this molybdenum target has a very low atomic number. So its characteristic X-rays are produced right down here, right around 19 kVp. Okay, so, and as you can tell, because you use lower kVps, we have a lot less X-rays actually being produced overall. Okay, so we had target material will change the discrete portion, which is this line, at a specific time. It represents a specific energy level, and for us, for tungsten, we'll look at it and see that the characteristic, the discrete portion, is at that 69.5. Okay, so, and everything else below here is all BREMs. Okay, if it's not happening at that discrete portion, it's not representative of characteristic. Everybody okay with that? Okay, all right. Making sure, sometimes that causes a little problem. Okay, so we and when we're talking about the quantity, since we know that BREMS X-rays are not energy dependent, as our MA value goes up or our overall mass value goes up, so will the number of BREMs, pretty much directly. Okay, so the more X-rays I produce, the more of them that are BREMS X-rays. Okay, and until I hit a specific energy level, that 69.5 in a tungsten target, I will not have characteristic X-rays. So anything below that energy threshold, I won't be producing characteristic X-rays at all. So I have to have a KV, basically 70, to produce any characteristic. And once I get energy that is higher than that, it can be slightly higher than that 69.5, but only slightly, because otherwise it'll represent more BREMS X-rays. That's why BREMS is a continuous spectrum and happens above, below, and around, and even during that time we're still producing BREMS X-rays. So not being energy dependent is actually a good thing for us. So we rely a lot more on BREMS X-rays than we do on characteristic X-rays. Everybody okay with that so far? All right, so everything that affects quality, we're talking about energy. So, and so we know kVp is the measurement of our beam energy. The energy is responsible for the penetrability of the X-ray, and that's also a measure of the efficiency of our equipment. So all those things will affect this x-axis. Okay, it doesn't mean that they won't affect the y-axis. It just means that it will affect the x, as that they'll affect the x as well. So we have KVP, generator phase, filtration. Target material is just discrete only because it'll only happen at a specific time at a specific energy. Okay, so if I have something that is affecting the amplitude of the spectrum, if it's affecting the amplitude of this spectrum, then it is affecting what? It's a change in what? Quantity or quality?
Quantity.
Mm-hmm. And if it affects the energy or efficiency, then it's affecting the
Quality.
okay. So quality change are represented by a shift in what direction? Or directions, I should say.
You said quality,
Yeah, quality.
side to side, the x-axis.
Okay. Yep, very good. Yeah, shifts left to right. And amplitude is a movement up and down, right?
Yeah.
Okay. Is everybody okay with that so far? I'm going to assume. Go ahead.
Somewhat okay.
Okay. Hey, honesty is a good thing. I'm trying to see where. So we'll go back a little bit to the beginning and we'll talk about each one specifically. So we'll go back through. We know emission spectrum here, okay? Amplitude, number of, up and down. Energy of, shift right and left. If it's something that affects a discrete portion, this is a discrete curve, okay? So this represents what characteristic is, okay? So characteristic is dependent on the energy of a specific K-shell. So every element has a different K-shell binding energy, okay? So this number is representative of tungsten's characteristic K-shell binding energy, okay? So that is specifically energy dependent. So if we used gold, we would expect to see that discrete portion move over this way. If we use molybdenum, it goes way over here because molybdenum has a much lower atomic number, so K-shell binding energy is much lower. We feel good with that so far?
Yes.
Okay, and we know that BREMS, that's representing the bell curve, okay? So BREMS happens at any energy. So whatever I set my KVP to, I'm always going to have BREMS X-rays, okay? And that's always going to be the lion's share of my X-rays. Sometimes it'll be 100% of my X-rays, depending upon the KVP I pick. Does that make sense?
Yes.
Okay. Hey, you're the only one answering me, Chanel, so I'm letting you speak. If other people are gonna say something, then they can say it then. Now here, this one's a good one because this shows us what happens when we change our KVP. Okay, so this first curve, the bottom curve, represents 72 kVp. And again, you see that discrete is right at the 69.5. For the 82, that does not change because the target material didn't change. So that stays right at that 69.5. So that won't move anywhere, okay? So, but the curve itself shifts to the right because our actual peak energy is 10 kV higher. So we produced more quantity, right? You can see even at the low end, we produced more quantity, but the majority of the higher quantity comes to the right. So this actually affected the overall position. It affected the amplitude, right? We have more X-rays. So we had an impact on amplitude, but then we also had that change in the position, that shift to the right. We had an amplitude change and a change in position. Everybody feel good about that?
Yes.
Okay, so that's an important thing to recognize with KVP because we're always telling you guys when you change KVP, you affect the quantity and the quality of the beam. So it's real important to recognize that because we do shift the number of higher energy X-rays. We still are going to have low energy because we're only changing KVP. If we change filtration, then we would have that movement on the front end of the curve versus on the back end of the curve. So just recognize, so if we went down, we're going to reduce amplitude. If we went from 82 to 72, we have that reduction in amplitude and then that shift to the left in position going from a higher kV to a lower kV. Everybody okay with that so far?
Yes. So when you shift it to the when it shifts to the right, is due to filtration?
With filtration, yeah, but it's going to be this end that's good that would shift. That front end because we're getting rid of low energy. But I'm going to get back to that. I just wanted to tell you that when I was looking at it is because we have that, we lose low energy photons.
Okay.
Okay. So this one is our voltage generators. Okay, so this is, am I using a single phase? Am I using a three phase? Am I using a high frequency? So KVP left constant, okay? The only thing that they changed was the generators that were used. So single phase, we know we go from 0 to peak to 0 every single time. So very inefficient, 100% voltage ripple. So this is going to be our worst one. It'll have the lowest amplitude and it'll have the lowest quality, okay? So on this, you see how I'm showing you, and now look, here's your amplitude here, right? And here's where our quality is. So then we go up to a three phase, we increase amplitude, right? From single phase to three phase, we increase the amplitude, but we also got more higher energy X-rays. So that represented that shift to the right as well. So increase in amplitude and a positional change, but not at peak energy. Okay. So just remember that like overall mass of X-ray energy is moving, but the peak energy never changed because we didn't change KVP. High energy, again, we went up in amplitude for the high frequency. So we saw that shift in amplitude. And again, we have that shift to the right. We have more higher energy photons, but never go above that peak energy. Yes, Amy?
So the generator is going to affect both the amplitude and the position, right?
That is correct. Yep.
Okay.
And that's why when we go from a single phase to a three phase or a three phase to a high frequency, why our technique is affected. And we have to reduce the technique that we're using because we are producing, with the same technique, we're producing a higher quantity and quality beam. You good with that so far?
Yes.
Okay. So this is kind of basically just taking each and every one of them and taking them apart so you can see what's happening. This one, again, MA, we're just talking about a change in the quantity, the amplitude of the X-ray. No shift in, no real shift in position, just amplitude. That's probably the easiest one to understand. Okay, now this one with the 2 millimeter, this is where we're talking about filtration. So that's why I say more on the left side of the curve, because we talk about all these X-rays that we got rid of. So we dropped the amplitude, but these were all X-rays that were going to result in patient dose, right? So we reduced the quantity of X-rays, but with getting rid of the low energy, we hardened our beam because now the majority of the X-rays fall like in this area. So it has a narrower latitude of energies. And you can see that that represents that little bit of shift to the right. So the overall energy of the X-rays that we're preserving are higher energy X-rays. But again, the max kVp, your kilovoltage peak is still your kilovoltage peak. So if we said that this ended at 95, then we would say the kVp was still 95. It didn't get higher because of the filtration, just the average energy of the beam is improved. Okay, that's just average energy being increased there. And then otherwise than that, we know that the quantity is reduced. Everybody feel okay with filtration?
Yes.
Okay. Okay, just trying to make sure that's target material there. I'm trying to make sure I've hit all of these. And these are the last ones, but these are actually pretty good ones. I like them because what they're doing is on this one, they're showing you kVp of 50. Okay. And then you have this area in here where we say here's the average energy of the beam itself. Okay, so the most number of photons are going to be in this energy range, right? And then here we actually have 100 kVp. So you see how the shift in the average energy moves over. So now the shift in the average energy is around 30 keV as an average energy versus being at the low side on 20 as the average energy at the 50 kVp. So not only did we significantly increase the amplitude of this waveform, we also significantly increased the quality. So we shifted to the right on this 100 kVp waveform. Does that make sense?
Yes.
Okay. And this last one I thought was just pretty demonstrative of the different photon energies again. So we all started, everything started at 0. Here's your 50 kVp. So obviously showing lower amplitude and the lowest quality, because the quality side cuts off at 50 kVp. And then at 75, again, that increase in amplitude, and the shift to the right, the increase in quality. And then 100, again, still more amplitude, and the shift to the 100 being the maximum energy on the quality. So each one of these shifted to the right as we changed the energy that we picked as our peak energy. We okay with that?
Yes.
All right. Okay. So now at this point, I'm going to go ahead and be quiet for a second and see what stuff you might want to ask me questions about the emission spectrum. What you're still not getting. Okay. Well, that's fair. You can't think of anything at the moment. Are you okay with the information that we went over? Is there anything that I maybe need to explain differently or attempt to explain differently to make it make more sense to you? And sometimes it's just breaking everything down to the bare bones and attacking it that way. And that's why when you're newer, I try to attack it that way and go from basics and, move through. Okay. And you do have one of your well, you have a couple of your formulas that are represented here when we talk about doubling the mass, doubling the quantity, and then when we talk about KVP affecting both quantity and quality, and we say, well, when we do a 15% increase in KVP, that it represents that doubling of the mass radiographically. You guys don't have that representation very much anymore, because with digital equipment, contrast is maintained. So you don't see that technically on your film, but it does actually affect your EI number. But typically changing the KV, when you change it that 15%, you will change your EI number, but it won't represent such a large increase in patient dose, because that's why we choose to increase the KVP by 15%, because we make a more penetrable beam, so more x-rays go through the patient and interact with that IR than are absorbed by the patient. So we affect the attenuation of the X-ray beam. It's hard sometimes when you guys can't see stuff like that anymore, so it's like, eh. Do you have any more questions for me that you have right now? I mean, granted, if you come up with stuff, you can always post them, or you can ask me in person. I don't have a problem with that. But I did have that physics section in there so that you could post questions. One thing that I want you to recognize when we talk about changing the generators, and I told you how going from one generator to another, I knew it was right there. Okay, when going from one generator type to another, remember I told you about when you go from a single phase to a three-phase, you have that choice of where you could cut your mass value in half, or you could reduce your kVp. And basically we're talking about, it's about a 12% reduction. So we talk about going up or down 10 kVp. Whereas when we switch from a single phase to a high frequency, it's so much better that it represents about a 16% increase in kV. So there we can either reduce the kVp by 16%, which would do nothing to decrease patient dose. We could reduce the mass to a third of the original mass, and that would represent reducing the patient dose to a third of the original patient dose. So that's why I'm always telling you about changing. If you have to increase something, increase kVp. If you have to decrease something, decrease mass. Anything else I can answer for you at this time? Okay. All right. So then when we, did you have any problems with any of the formulas that have to do with X-ray emission? I know you dealt with X-ray quantity and mass, and so you know that if mass goes up, patient dose goes up, right? We're good with that? And if mass goes down, patient dose goes down. Okay, so you know that's a proportional relationship, and it's a directly proportional relationship. The other one would have been, and you should have dealt with that in 1418, would have been about intensity or quantity and kVp, the only relationship that those two share. And that's the intensity to kVp squared. Everybody familiar with that formula?
Yes.
Yes, okay, good, because that's a real important one, because that one actually shows you that when you make changes to kV at normal levels, so using 15% rule, that it represents a huge reduction in patient dose with the mass changes to that you would compensate with. So going up in kV and cutting your mass in half, and the change in patient dose is incremental in comparison to a mass change. Everybody good with X-ray quantity and distance, and what law is that?
The inverse square law?
Yeah, it's the inverse square law. Okay. So does can you tell me does distance affect the energy of the X-ray?
Yes.
Hmm.
No.
Yeah, that's a no, because the energy of the X-ray would, and here's our thing: the energy of the X-ray would remain constant into basically into infinity if there were nothing to interact with that X-ray photon. So the only time the energy is changed to that X-ray photon is with it interacting with matter, whether that matter is a patient and that X-ray gets absorbed or scattered, or maybe it's a high enough energy that it goes right through. Then you might have a grid that possibly would intercept it, or it interacts with the IR, resulting in an X-ray image. If it still had enough energy to continue on, that's why we have primary barriers, because that primary barrier is there to attenuate that X-ray still further, and there should be enough layers that it should absorb the majority of the X-ray photons. Okay, so distance will never affect the energy. We have to put things in the way of that X-ray beam to reduce the quantity of X-rays by getting rid of energy, absorbing some of its energy. That makes sense that way?
Yeah, thank you.
Okay, no problem. Yeah, that's an important thing, because though you were not the first person, that's why I was waiting for an answer for that, because you're not the first person who's ever thought that way. And when we talk about um, intensity of that beam, which is quantity, right? The quantity of the beam being reduced with distance. The reason why the quantity of X-rays is reduced with distance is not so much that X-rays just disappeared. It's because we have a divergent beam. So when we're saying the quantity that would hit that imaging plate, the more distance, the more the beam has a chance to diverge, so the larger the area that that beam covers. So if you talk about 12-inch by 12-inch square in the middle of that field, less X-rays would interact with that 12-inch square of material, because more of them would be more spread out over a grander area or a larger area. That makes sense?
Yes.
Okay. All right. Yeah, that it never hurts to go through it in a formula level, because sometimes that's where you pick up problems that people are having, is by dealing with it at a formula level. So then we have the direct square law, which is how we compensate for that beam divergence at different distances, right? So if we were using a 72-inch SID and we reduced it to a 40-inch SID, then we would know that our mass would have to be reduced, right?
Yes.
Okay, and if we did the opposite of that and went from that 40-inch SID to the 72-inch SID, we would have to increase our mass. I say we can also increase KVP, but you know that I'm always going for increase in KVP, but you would need to have that increase in mass to compensate for the longer distance and the divergence of the beam. Just trying to make sure that I have dealt with anything and everything that I can think that. Oh, and one of the things too, and this should make sense to you, is when we increase filtration of our beam, and now I have an energy that is more compact, a harder beam. So like say all my energies are compacted in a 25 to a 75 kVp range. That would be that harder beam because I got rid of the lower ones. So this beam would be a more penetrable beam. So if I make it a more penetrable beam, then I need more protective barrier there to be able to absorb those X-rays because the overall X-ray energies are higher. Does that make sense to you? Okay. And Chanel just gave up on me, huh? All right. So I just wanted to make sure because that was probably one of the last things. So if you still don't have any questions for me, I'll go ahead and close out with that. I did record this, so if there's anything that you want to go back and listen to, if you think it's going to help you, feel free. It'll be available probably within about a half hour or so of when we shut this down. Just depends on how fast they get it into the recorded sessions, but it doesn't take real long. So if you have no more questions for me, I'm going to go ahead and, oh, good. I'm glad, Amy. I hope so. I hope it did help. I'll go ahead and close this out for now. And y'all go ahead. Remember, everybody's got a lot of work still to do. So let's get those rad reviews done. Get the workbook done. We should be wrapping up the workbook. I know it's only week 3, but you should be well on your way to be that the chapter should be done, and you should be working on self-test by the end of this week and into next week so that they're all done. Okay? So work hard, have a good day, and I'll see you guys tomorrow on ground. Thank you.